So we want to build to talking about magnetic fields, but I want to start with a review of our treatment of electric fields and then build to magnetic fields by analogy. That electric fields, of course, arise from various arrangements of charge. That charge gives rise to an electric field, and then that electric field can exert a force on a second charge. These would be different charges. That we developed Coulomb's law for getting what the electric field was from various arrangements of charge, and then we went on to the much more elegant Gauss's law for getting the field in those special arrangements when the field was sufficiently symmetric. Now we want to move on to the magnetic fields, and of course they do not arise from a charge but rather from a moving charge, what we speak of as a current, and that current does give rise to a magnetic field, and that magnetic field can then act on another magnetic field and cause force. And again, we have first the kind of sledgehammer approach like Coulomb, which we are going to learn right now. It's called Biot-Savart's law, and then we will move on to a much more elegant treatment where there is sufficient symmetry in the field, called Ampere's law, which will correspond to Gauss's law. And that will be the second of Maxwell's equations that we have learned. But let us go back to Coulomb's law. And I would like you to put on your worksheet a statement of Coulomb's law, not for force but for the field, and rather than the whole field, let's go for an infinitesimal field, which would rise from infinitesimals of charge. So if you could just for the practice of it all, if you could state Coulomb's law. And then I'm going to put it up here on the screen, but you need to take the opportunity to practice what should be inside of your head. So we go on. That the statement that you wrote down on the worksheet, I hope, looks something like this. Perhaps it looks better without all these slanted fractions. But we never really paid attention to the fact that this quantity here is a vector quantity, which I have sort of emphasized by making it bold. But this is a vector quantity on this side of the equation. Over on this side of the equation you have constants, you have charge, which is a scalar, and you have r. The spatial position vector is a vector, but if you square it, that's going to be a dot product. It would not be a cross product because r would be completely parallel to itself. So if you did the cross product, you would get a 0. So this must be a dot product or a scalar product. That everything over here is a scalar. So how can there be a vector quantity on this side? Well, it's time to fix that. And the fix that we will do is to just add another radial vector here, and in the numerator and the denominator. And this quantity here will be a vector, and so now we've got vector quantities on both sides of the equation. That may seem kind of goofy, but that's definitely what we're going to do, and it is a perfect analogy to what's coming up with Biot-Savart. That in your book and in many uses, they will instead write something like this. Instead of dqr as a vector over, here it is, dq r as a vector over r cubed, what you will see in the book sometimes is, instead, with the 1 over 4 pi epsilon out front, you will see dq the r unit vector over r squared, with the 1 over 4 pi epsilon out front. And I can't fault you if you do that. Please be very sure that I can tell you were talking about a unit vector here. I would much prefer this r cubed in the bottom and an r up top, but if you do it this way, I cannot fault you. I'll just be irritated with you. But it's absolutely correct to write that instead in your statement of Coulomb's law. Please notice that the direction of this r, or of that r unit vector, is going to be determined by the direction of E. It is not going to automatically go away. For one thing, well, that is a point charge. But if it was a negative point charge, then, sure, we could have the r go away, and because this part here is negative, that would have this going inward. Yeah, I'm sorry to think about these things in the middle of a lecture. I thought I was very clear that it was awkward, but it's not. That this is, the direction of this would be away from the charge. But if it's a negative charge you put there, then it's going to be negative away, which is the direction of E for a negative charge. Now we will take this idea, and from it I'm going to develop an expression for the magnetic field from an infinitesimal of current. What does that mean, an infinitesimal of current? What we will do for an infinitesimal of current is take the whole current, and then I will take an infinitesimal of distance along the wire, along the path that it is flowing. So this quantity here is going to correspond to an infinitesimal of charge. And this quantity here will give rise to an infinitesimal of magnetic field. And it looks like this. That we are going to have, instead of dq, we have ids, and then the r, and the r, and the r cubed, and the r cubed. Notice this time I do not want to have this be a unit vector here. That this is to be a vector quantity here, and now I am ds is a vector, and r is a vector, and so it needs to be the vector product, the cross product of those two. And of course, it being a cross product, the order is very important. You need to start with the direction of ds. Yo, what is the direction of ds? The direction of ds is determined by the direction of the current. The current, of course, is not a vector, but it will assign its direction, even though it's not a vector, to the direction of ds. And you need to do a right-hand wrap from the direction of the current into this vector, which, as was the case up here, will be going radially away from the wire, and that will give you a statement, the direction of B, and this will get you the magnitude of B. Notice also that the permittivity constant has been replaced by the permeability constant. That it's still a 1 over 4 pi, but instead of an epsilon in the denominator, we'll have a mu naught in the numerator. And it's very important. Here it's supposed to be an epsilon naught. It's the permeability of free space, and this is the permittivity of free space. But this time you absolutely must put the naught, because we will run into many other cases, such as the magnetic dipole moment, which just use a mu. So because there's all those other uses of mu, you must call this mu naught. This is called Biot, which the book says is pronounced like Leo and Bazaar. Okay, don't sound like an idiot. Say it right. And that is what we're going to work with. For example, I would like to know what the magnetic field is from an infinite wire carrying a current I at this point P that is capital R away from the wire. So what do? You cut up this current into little infinitesimals of current, ds. And each of those little infinitesimals of current will give rise to an infinitesimal of magnetic field. It'll look like this. That this infinitesimal of magnetic field, which comes from this little infinitesimal of current, is going to be mu naught over 4 pi times the current ds cross r divided by r cubed. And we have to have this so that we can have a cross product. And that IDS cross r is going to be IDS r sine theta. So I replaced the cross product by that sine theta and the magnitudes of those two. So now we can go back to an r squared. That this was going up was the direction of that vector, and this r was going this way, and so you need to put them tail to tail. So properly the angle should be this angle up here, but the sine of this angle up here is identical to the sine of this angle down here. That's a little more convenient for me to work with. And then what we're going to do, well, I'll simplify this a little bit. That the sine of theta then would be the opposite over the hypotenuse. So I have gone from the r cubed to an r squared, and then the sine theta, this is not in the denominator, that's capital R over the hypotenuse. But then r, of course, is equal to where we are. We're about to evaluate an integral, and I want to do it with respect to s, so I need to do the fact that little r is a function of where you are along the line, and it's going to be equal to the square root of s squared plus r squared. But we have r cubed, so it's that s squared plus r squared raised to the 3/2. All right, now we have what a little infinitesimal magnetic field is from this one here. But what I want you to do on your worksheet is to tell me what direction that infinitesimal of magnetic field would be for the infinitesimal of current at this location. What is the direction of the magnetic field right here? And then we're going to add them all up. And I hope that you are convinced that as you went to different positions along the line, while this quantity s is going to change, and so that radius vector is going to change, but the direction, I hope, would stay the same. Whatever it is you said was for this dB would be the same for all the other dBs, for all the other infinitesimals of current. So I'm going to add them all up to get what the magnetic field is there, and what I'm going to do is go from the middle of the wire out to infinity instead of going from negative infinity to infinity, and so I'll do that twice. And then I put in this quantity here, which is an integral to be evaluated, that we need to do a substitution, a trig substitution for s, and if that's what S is equal to, then ds is equal to this, and that's going to mean that I'm going to have to get a I'm going to put that in for S right there. We're going to have a nice trig identity. But this r here, r times ds, I need to pull this r outside the integral. And then I will replace ds. So I'm going to have a 2 and a mu naught over 4 pi times r and times I. All of those will be pulled outside the integral. There you go. The 2 and the 4 go together, give you that 2, and you're left with evaluating this, which evaluates very nicely. And then I substituted I replaced r tan theta with s again, and you get back to this expression. You work it out if you don't believe me. So here is the result. We want to evaluate that from 0 to infinity. Of course, if we let s equal infinity, that what you're going to end up with here is a 0. No, you're not. Yes, you are. No, you're not. 1 over s on the top, 1 over s on the bottom. I end up with a 1 plus r squared over s. And as s goes to infinity, this would go to 1. And as s goes to 0, this goes to 0. So you end up with just this quantity when you evaluate it from 0 to infinity. Mu naught I over 2 pi r. Which is and of course there is this direction as well, which you have established. This is a very powerful formula. We're going to develop it with Ampere's law, and it's going to be a much prettier journey than we had here. But it is a very important result to remember. You're going to run into a lot of wires carrying current, and you're going to want to know the magnetic field at some distance away from it. And it has this lovely mnemonic that, after all, 2 pi r is a circumference, and we represent circumference with a c. So this says buoy over the sea. What could be I think that's perhaps the best mnemonic of all. And you were there. I want to caution you to be very careful about intrinsic and extrinsic fields. This would go for electric fields as well. That if you have a charge, Q, that it will give rise to a field, which I will call E1, but this field that it creates would not then exert a force on this charge. That this creates a field, we would call that an intrinsic field, and it would not exert a force back on the thing that created it. It has to be a field from someplace else. If you have a Q2, then this field, which would be extrinsic to Q2, would exert a force on Q2. But it would not exert a force back on the thing that created it. The same for magnetic fields. That here you have a current. I hope you recognize that as a current going into the page. And from it, there is a magnetic field. You, in fact, know what it looks like. You use a right-hand rule, right? And you put your thumb pointing away from you, and you find that the fingers of your right hand are wrapping that way, that this current-carrying wire creates a magnetic field which encircles the wire, and its strength would depend upon R, in that buoy over the sea sort of way. But that would be a field that was intrinsic to this current. And this field would not then exert a force on this current. There would have to be another wire, perhaps carrying a current towards us, for which this field from this wire here would be an extrinsic field, and it would exert a force on that wire. Okay, I probably labored over that long enough. Another result that is just nice for you to have in your bag of tricks is to again talk about the current from a infinite wire. An infinite current gives rise to a magnetic field, but suppose you only did half of the wire. And one way to do this would be to have a wire. Let's see if I can do this in one swell swoop. If you had a wire, no, it's not fat enough. At any rate, if you had a wire that had a right angle in it like that, then this part of it would not create any magnetic field here. That all the magnetic field would be created from this wire here. And if it was half of an infinite wire, then the magnetic field you get only here above the end, not here, but above the end, the magnetic field you get is half the result you got before, half of buoy over the sea. That's a very cute result to have in your bag of tricks. Now I would like you to do a problem using Biot that we have wires, comes in radially. Here is the point we're talking about, is along this line and that line. I didn't do it so well. The current comes in, goes around this arc and off like this, and I would like to know what the magnetic field is at the center of that arc. First of all, on your worksheet, will you put what the contribution to the magnetic field here at the center is from these two sections of wire? And then added on to that, I want to put the contribution from this arc of wire here. And of course, what I need to do is to, and the arc is a third of the way around a circle. I need to break this into little infinitesimals. A little small distance ds along the wire times the current flowing there. But to evaluate this integral, I don't want to go from the beginning to the end of that arc. I think you would do much better to replace IDS, this infinitesimal of current, with a little, oops, that's not what you were supposed to do. A little, oh, pooch you. A little wedge here. Let's get rid of the yellow. Probably I'll get rid of everything. We'll see. Oh, yes, everything. We'll try again. What we want to do is take that ds and treat it as a d theta times this capital R. And this would be very nice to evaluate. You could get your limits of integration very nicely for that. Again, what you're going to do is to take that infinitesimal, and I would like you to pull it out of your head. And if you can't, then you turn back in this show to find out what Biot is. But see if you can take the fact that the magnetic field would be the sum of all the little infinitesimals of magnetic field, and then replace this from the expression which is Biot, and then make this kind of a substitution in there, and then get nice limits of integration, and get me a value for the magnetic field. The magnetic field from this part, plus the magnetic field from that part, plus the magnetic field from that part, to have what the magnetic field is there at the center. And when you finish that, just consider if you changed your limits of integration so that you went all the way around a circle, and see what results you get there for the magnetic field at the center, only at the center of a circular current, I. Okay. And that's the end of the show.